If you would recall, we've been looking at triple integrals in rectangular, cylindrical, and spherical coordinates. We have our basic maneuver where we integrate over some solid W. Here we are describing the solid W. And we had 3 different dVs depending on how many angles we were using as coordinates. So the main thing that we want, here's the TLDR. For cylindrical coordinates, we need an extra factor of R. For spherical coordinates, we need 2 extra factors, rho and rho sine phi. Those turn our angles into distances so that dV can be a volume. This is regardless of whether we want to actually calculate dV as a volume, whether we're thinking about it as a volume or not. It turns radians into whatever units we have for rho or for R. So yesterday I proposed the problem of taking your basic shapes, your intervals, a rectangular box, a cylinder, and a sphere, and describing them in all 3 different kinds of coordinates and what we would have to do to make that happen. And then it also occurred to me that along with that, we should not look at the entire thing all the time. So we spent a lot of time with this sphere of radius 5. And we set up a triple integral to represent the volume of the sphere. So I'm integrating the function 1. That'll give us the volume. Remember that integrating the constant function 1 gives you the size of the solid or region or interval over which you are integrating. So integrating the triple integral over W of the function 1 will give you the volume of the solid W. But I feel like I kind of glossed over the thinking behind the range of values for rho, the range of values for theta, and the range of values for phi. So we should let's take this sphere of radius 5 and look at smaller parts of it. See what happens if we look at different chunks of the sphere. So we have a sphere. So we're thinking about a sphere. Let's see. My sphere is not going to be very spherical because I'm kind of freehanding a sphere, and they tend to get a little bit squishy. So right now we've got a triple integral for this entire sphere. And I did describe these as intervals, but they're not the same kind of intervals that we think of when we think about intervals of real numbers. I describe them as intervals because it's just our variable is between 2 constant values. Nothing is changing its shape. It's always the variable between 2 constant values. So let's imagine our sphere of radius 5. So we have these 3 ways we could describe what each of the variables are telling us. We know that the rho is going to be the distance from the origin. So rho is measuring from the inside to the outside, from the innermost part of the sphere to the outermost part of the sphere. And if I want a solid sphere, that will be all the values of rho. If I restrict the values of rho, if I, for example, instead of integrating rho from 0 to 5, I integrate rho from, say, 4 to 5, Then I'm going to have a spherical shell with a spherical inside. So if we think about rho as measuring from the inside to the outside, if I imagine restricting rho, instead of going from 0 to 5, rho from 0 to 5 will give us a solid sphere. But if I just look at rho from 4 to 5, I'm going to take a sphere of radius 4 out, and I'll be left with a spherical shell. So if I restrict rho to be from 4 to 5, I'll have a spherical shell. With an inner radius of 4. And an outer radius 5. So we're not slicing it the same way we would when we slice an interval on dx, dy, or dz. We've got to remember what the graph paper looks like in these alternate coordinates. So I'll have a cylindrical shell with an inner radius of 4. So there'll be a void inside with a radius of 4, and then it would be solid from 4 to 5. So we'd have an inner radius, a spherical shell. This is because rho is the distance from the origin. So that's measuring from inside out. That's the direction on the graph paper for cylindrical coordinate, per spherical coordinate. For theta, we could do the same thing. We could think about what would happen if I restrict my values of theta. If we go for theta from 0 to 2 pi, that's going to be theta all the way around. So theta from 0 to 2 pi, I'm thinking of that as all the way around, starting here at 0 and going all the way around to 2 pi. So theta from 0 to 2 pi is all the way around the circle. That's what I'm thinking of here. 0 less than theta less than or equal to 2 pi. We're going all the way around the sphere. But if we restrict the values of theta, then we'll only get pieces of our sphere. But we have to think about how those pieces are going to show up. So if I restrict my values of theta to be, let's say, from pi over 4 to pi over 2, that's going to give us a slice above and below the first quadrant in the xy plane. So if I go to theta from pi over 4 to pi over 2, instead of going all the way around, I'm going to want to go at pi over 4 and pi over 2. So here is going to be my theta slice. Theta equals 0 is at the positive x-axis. And theta equals pi over 2 is at the positive y-axis. So if I go to pi over 4, which is halfway in between, I'm going to get this slice, like slicing an orange. Now I kind of really regret making this the green part because now my orange is green. Okay, so it's not a slice of orange, it's a slice of limes. Which really changes what happened at the soccer game. I don't know if that still happens, but like at the soccer game, one of the parents has to bring a big bag of like orange slices. You can tell the parents that went to a party school because they bring limes. And you gotta tell them, hey, we're not giving shots to 8-year-olds. But we're not thinking in terms of rectangular coordinates. We're not going to have rectangles. We got to think about what the slices are going to look like. And if I look at the slice from theta from pi over 4 to pi over 2, here at a 45-degree angle, that's where theta is going to be pi over 4. So instead of going all the way around, we want to think of 0 to 2 pi as going all the way around. We're only going from pi over 4 to pi over 2. So we're getting 1/8 of the circle. Or sorry, of the sphere. Now, if we just wanted the volume, we just find the volume, 4/3 pi r cubed, and then divide by 8. So pi over 6 times r cubed. But that's not the issue. The issue is understanding how spherical coordinates work and what the intervals are telling us. Spherical coordinates, to get our up and down, we use phi, and phi is the angle measured from the positive z-axis. So phi is measured from the positive z-axis. So up here at the positive z-axis, here's where phi is equal to 0, and then down here at the negative z-axis is where phi is equal to pi. It sounded like I was going to say something after that, but I wasn't. So that's where phi is equal to pi. That's our typical range. That's all we need for phi from 0 to pi, because 0 is at the top. If we sweep down to pi, that gets us down to the bottom. If we go all the way to 2 pi, if we go all the way around on phi, we're going to get the front half and the back half twice. We're going to be double counting. So from 0 to pi over 2, that's going to give us the top. From pi over 2 to pi is going to give us the bottom. If I want both sides, that's covered by theta. So we're going to keep our phi from 0 to pi for the top and the bottom. This doesn't mean that we'll never have negative values of phi, or that we'll never have values of phi after pi. It might at some point be convenient for us. So for example, if we think about the cosine function, if I have cosine and cosine, if I have a cosine inverse function, I want to go from 0 to pi. That's the most convenient two quadrants to use. Our cosine inverse, we've decided to go from 0 to pi. But when the two quadrants what we pick for sine inverse, because of the way sine looks, the two quadrants that we pick are first quadrant and fourth quadrant. First quadrant is our positive quadrant. Fourth quadrant is our negative quadrant for sine. And we pick first and fourth because that's where we can go from negative pi over 2 to pi over 2. So if we're going to be using cosine inverse and sine inverse, then we're going to want to be more mindful of our angles. This is one of the things that makes describing things with angles more complicated, because the angles just keep going around, and I have an infinite number of ways to describe a particular location. But for a simple setup like this, we're thinking 0 to pi over 2 is covering the top. Pi over 2 to pi is covering the bottom. So the top is 0 to pi over 2. And the bottom is from pi over 2 to pi. So phi from 0 to pi that's going to give us from the top to the bottom. So if more kids showed up to the soccer game than we had attended, and we just take all of our lime slices and start cutting them in half, one kid is going to get the 0 to pi over 2 slice, and the other kid is going to get the pi over 2 to pi slice. So if I have pi over 2 that's going to be our bottom hemisphere. So here, theta is pi over 2. This is also the xy plane is where phi is equal to pi over 2. So it's not just this location here on the positive y-axis. The whole xy plane is where phi is equal to pi over 2. So if we run phi from pi over 2 to pi, that's going to give us the bottom half of that slice. We want to make sure that we understand how these intervals work when we're dealing with intervals that are angles, not intervals that are just distance, where it's all distance. If we think about a side view, let's think about a side view. Where here would be the positive y-axis. And down here would be the negative z-axis. Looking at it from the side, we won't be able to see the change in theta. We will be able to see the change in rho. Here's where rho is equal to 0. And out here is where rho is equal to 5. here is where phi will equal pi over 2. And then down here is where phi will equal pi. Down here, rho is also going to equal 5. So if I put some of these restrictions on, now that I've got a side view and I can really clearly see where what rho is doing and what phi is doing. I've squashed out any chance of viewing what's going on with theta, but let's just look at it from the side here. If I restrict, say, rho from 4 to 5, I'm going to have this shell running around the outside. And if I further restrict phi, let's say I'm going to cut at a 45-degree angle here. Here's phi halfway between pi over 2 and 2 pi over 2. So 1.5 pi over 2, otherwise known as 3/4 pi. I can see what's going to happen if I start cutting things down. We're trying to imagine what the graph paper looks like in spherical coordinates. I guess it's not graph paper because it's not flat. We're describing three-dimensional coordinates. So when we think about rho going from 0 to 5, we're thinking about this segment that's 5 units long. And if we think about phi going from pi over 2 to pi, we're thinking of taking this 5 units segment and rotating it down. Take this 5-unit segment, take this 5-unit segment and rotating it down rather than just cutting off values with vertical lines. When angles are our coordinates, we've got to think about arcs rather than horizontal or vertical lines. Rather than think about horizontal, vertical, or vertical lines or planes, we got to think about arcs. So when we have a spherical cake, normally the way we'll cut it up, I mean, like all the time, right? Remember the last time you had a spherical cake. When we cut it up, we just use a knife and we just cut planes through it because we're not following the graph paper. We're not cutting it according to the graph paper. Now, when we have a cylindrical cake, we do cut it according to the graph paper for the most part, unless you're at my house, because I cut it differently. But If we imagine how we cut a pizza, we cut that according to the graph paper. We cut all our cuts go through the center. We're cutting at different values of theta. So in cylindrical coordinates, if we have a cake, you're cutting the cake at different values of theta. In spherical coordinates, if we had a spherical cake, I don't know how you would do that, but you cut it into spherical, you cut it for different values of theta. So we can see that theta is making these lines, but if we are cutting with spherical coordinates for radius, now I guess we would need, I don't even know, different size melon ballers? Is that what we do? We have to like scoop out little spheres. That would be weird. I don't know how that would work. You can cut a cylindrical cake. So important question, how else does one cut a cylindrical cake? You can cut a cylindrical cake with rectangular coordinates. So since it's come up. So you have a cylindrical cake, right? These are the important issues, right? This is why you came to Calc 3. So you can learn some better techniques for cutting a cake. Now the traditional way to cut any two cylindrical cakes, because I'm going to cut them different ways. Now remember, our knife is just going to be our knife is in rectangular coordinates. Our knife is like a plane. It's going to put a plane right through the thing. Now the traditional way of cutting a slice of cake is to go through the center, like it's some kind of pizza or something like that. Remember, we don't call them pizza cakes, we call them pizza pies. But anyway, and you make these cuts through the center. Like so, you're cutting for different values of theta. I used orange and it should have been, that's fine, it's fine. It's Halloween, it's a pumpkin cake. But a cylindrical pumpkin cake, so it looks weird and distorted. It's like a Minecraft pumpkin. Oh, I guess that would be a block, huh? Make it bigger, zoom out farther. So this is normally what we do. The problem is it creates a void like this, right? So then you pull this piece of the cake out. And then like this inner part gets dry. So as an alternative, rather than cutting the cake for different values of theta, just go ahead and cut the cake for different values of x. Oh, sorry, I'm doing vertical. So cut the cake for different values of y. So you make a cut there. And then you make a cut there. And then you make a cut there. So you make the slices of the cake are cut out of vertical slices. Rather than cutting for different values of theta, cut for different values of y. And if these are too big, then you can also cut for different values of x. So you can also cut like these ones like down the side. Now, the reason that you would do this is that if you cut down the middle and then evenly space on either side, then if you don't eat the whole cake, because you're like some responsible adult that doesn't eat entire cakes. I mean, I don't know what the hell's wrong with you if that happens. Then instead, if you want to save some of the cake so it doesn't dry out, you just take the two pieces that aren't quite circles and just kind of push them together. And then it preserves, it keeps that inside from going dry. So at this point, you can do the important thing of pushing them together. So that's another way to cut a cylindrical cake. Just use x and y coordinates. Just cut using x and rectangular coordinates, despite the fact that the cake is cylindrical. We're cutting the cylindrical cake with rectangular graph paper, rather than cutting for different values of theta. So over here on this other side, So there's a cake cut on different values of theta. Over on the other side, that's a cake, that's a cylindrical cake cut for different x and y. For most cakes, like for most round cakes, cylindrical coordinates are the way to go. Because we got the cake is forming a circle, then we have like a circle of frosting around the outside. So R goes from 0 to 5, that's cake. And then R goes from 5 to 5.5. That seems like a lot, but it's fine. R goes from 5 to 5.5, that's going to be the frosting. Now, if we have layers in the cake, those are different values of Z. Z equals 0 is the cake that's on the plate. That's like the part that's going to get stuck. So after the cake, after you cut a piece of cake, that's going to be the part that's like stuck to the bottom. And you get to like scrape that up with your finger and eat that. If you're the one cutting the cake, that part is yours. It's like the center of the pizza, the glob of cheese that gets stuck in the center that leaks off. That if you're the one that cut the pizza, that part is yours. So for Z equals 0 to Z equals 1, that's going to be cake. And then from Z equals 1 to 1.5, that's going to be filling or frosting. And then from 1.5 to 2.5, more cake, and so on. And cake is nice and round. Theta goes from 0 to 2.5, but rather than cut different values of theta, just go ahead and cut it X and Y. You should do this with pizza as well if there are a lot of people. That way you can have smaller slices of pizza. Just cut the pizza into a grid despite the fact that it's round. The reason it's okay to do this is that you're not integrating the pizza, you're just eating it. So also, you just have more options if you do these rectangular cuts, right? Like the smaller slice of pizza gets cut like at a different value of theta, and it just gets harder to manage. Any questions? Did I skip breakfast this morning? What the hell? As far as slicing up round things, like if we have a spherical thing like a tomato or something like that, we just have to cut it with rectangular coordinates. I suppose no, you can make, I guess with a tomato, depending on how firm the tomato is, you might be able to cut in cylindrical coordinates. A good example of a nice spherical coordinate vegetable would be an onion. The different layers are different values of rho. Just don't look at the middle because it's all it kind of breaks down in the middle. Any questions? So onions are in spherical coordinates. Leeks are in cylindrical coordinates. No natural food comes in rectangular coordinates. Any questions? So more than just, yesterday we had, even though it's a very messy task, rectangles, cylinders, and spheres in rectangular, cylindrical, and spherical coordinates. Even though that's a messy task, it's kind of straightforward in that we're looking at the whole thing. And what we want to be able to do is capture smaller pieces in different coordinates. Any questions? Comments? Or snide remarks? How's everybody okay? The most important thing to do, there's not like problems you get right or wrong. You've got to start looking for where these coordinates would fit into different places. Where do we use spherical coordinates, cylindrical coordinates, rectangular coordinates? Where can we observe them? I look at my coffee mug here. This is clearly cylindrical coordinates. Here's a cylinder. I can imagine the cylindrical coordinates. What happens if I start chopping this up with different values of theta, different values of R? different values of Z. We've got globes over there in the corner. There's an excellent example of that's the sun in that little solar system model that's probably used for eclipses and stuff. It's got a little sun and a moon and an earth, not to scale because you wouldn't be able to see the earth if the sun and the earth were to scale. It would just take up too much space, especially if the sun was going to be that big and to scale. Crazy. But the sun has a light bulb in it, and so they had to cut a slice off the top of the sun. That is a great question. What if I take this sphere? What if I take this sphere and cut it flat across the top? So instead of cutting it rho from 4 to 5, I cut Z from 4 to 5. All right, so think about that. Look around at how your things are cut. Next time you are home and making dinner and you are cutting a tomato to put in your salad, think about those cuts that you're making in cylindrical coordinates and what happens to those shapes. Observe those shapes, how they're not like cylindrical slices, that they're rounded sides. That's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.